Code Code Milkers. We have binary tree maximum path sum today. So, given a non-empty binary tree, that's a node which can have a left or right child, and then that node can have a left or right child. Find the maximum path sum. For this problem, a path is defined as any sequence of nodes from some starting node to any node in the tree along the parent-child connections. The path must contain at least one node and does not need to go through the root. So a couple things to glean from that. That means that so we have our input here, we got 1 as our root node and then 2 and 3. For this case, it's going to be 1 down to 2, 1 down to 3, and we add all of those up. Now, and then that's 6. It goes to the root node, and we go to each left and right child, and all those summed together is the maximum path. So the path has to go from one, it can either be one node, or it can be, it starts at one node, goes through a root, and then goes down to a child, or it can just go from one to another. I'll explain that with a drawing. And then here we have a little more messy of a binary tree. We've got starting at -10, that's the root node. Then we have a left child branching off it with a 9 and then 2 leaf nodes into that. Then we have 20, 15, and 7. So the answer to this one is 20, 15, and 7 because those three summed together are the maximum path of that. So I'm going to share a whiteboard to draw something. Let's say we had that same example with -10. Oh, that's actually pretty good. Then 9, then 20. Oh, there we go. Okay, and 15 and 7. Now, in our case, let's say, can we have 20 and 15 be our maximum path? See, because this one's negative now. So the maximum path doesn't include -7 because 42 plus -7, 20 plus 15 is 35. Then plus -7 would be 28. We want the maximum path. We don't want the second maximum path. So in this case, it would actually be 20 and 15. Let's clear all that. Clear our drawings. And then I wrote an example down on my notes to show something else. Start with 2 as our root. And we start with 1 as our root, and then -48. And on the left side, we have 1. And then here, we have -46. So looking at this, we can see that we do not want to have -48 included in our maximum path because it's going to tank the max value. So if we start from the root here, we go into the left child 2, so it gives us 3 so far. If we added -48 to that, we'd get -45. That's not our maximum path. So it looks like 3 is the answer. But you might be thinking, can we include this 1 here in the maximum path? The answer is no, because you have to go through that node, the -48, and you'd have to include it if you included that as the path. So you can't bypass a node and not include it in the maximum path. And then another example would be just one root node of -3, and this one is obviously -3. We're going to come back to that problem. It's an edge case with this. Okay. Let's go back to, if I can get rid of this. Let's go back to explore LeetCode. Okay. So now I'm going to explain my implementation as I explain the code because it's easier to do it that way. So a great way to check what the maximum path is to do a depth first search, and that's what I did here with the recurse function. So outside of that function, in the max path sum function, which is called by the code editor, I have the result variable, and it's set to the first value in the binary tree, so the root val. And we know we can rely on that. We can call val on root because it will never be empty, so it can't be null. Then we just do recurse root, and we return the result. So you can glean from this that in the recurse function, we are modifying, we have side effects outside of the function. So it's kind of messy, but if you understand what's going on, it's predictable behavior. So if we are recursing and we reach a null node, so a leaf node, we just return 0. And it's 0 for a particular reason that we'll get to below. So if it's not null, we need to also see what the left and right values are and see if we want to include one of them or more in the max path that we have currently. So the return 0 here matters a lot because in that negative example, we have to use the 0 as a value to represent a leaf node. So we know that we've hit a dead end and we need to just return the max value of either the current node val or the result that's already stored. So if left is equal to 0 and right is equal to 0, that means are both the children leaf nodes. And we just get the max of that and reassign result accordingly. Next, if left is 0, which means our left child is a leaf node, which means the right is not a leaf node. It means it has a value of some kind and maybe some branching children off of it. Then we make the result either the current node val plus right, so that whole path coming down from it, or just the right one, or the result. Next, and I include right as its own thing in here because it could be the case that one node on its own is higher than every other maximum path available. And that one node in of itself is the highest, and it could be all the way at the bottom, right above a leaf node. So you have to include right here, and then also in here, left in the opposite if right is a leaf node. So we do the same thing, but for right. Actually left in this case. And then the else case is covering reassignment if both children are not leaf nodes, and we have to look at both child nodes, current node, and then the combinations of all of them. So right here is our actual return value for the recursing aspect of this. So if both children are leaf nodes, we just return the current node's val property, which is the number that it represents. Next, if left is 0, which means it's a leaf node, we either want to return the current node's value or node val plus right, because and that's the max between the two, because if we are recursing back up the tree, we want the current node to be either the maximum of itself or the max of its child included, because we want to get the most accurate maximum path recursing up to the root node. And we do the same for the left side if the right side is null. And then right here, this is kind of the else case. I didn't write else though. We return either the max of node val, so the current node on its own, the node val plus its left child, so all of its left children, or either node val plus right, so all of its right children. So we're going to run the code. And then see this root node is 3. Let's run it. Okay, let's submit. Let's see the time complexity here. Earlier I ran it, it got 40%, and then it got 80%, 71% now. Um, Overall, it's a good solution. It's pretty fast. Memory usage is going to be a little higher just because it's recursing. So we're adding stuff to the stack. Hope this helped. Have a good day.